and and how are the current experiments limited, and where do we need to go next? Okay, and so I have this line that I've been using that like for 20 years, one of my main public roles in the world with my blog and talking to journalists or whatever was just to say to people like, look, I'm sorry, quantum computing almost certainly cannot accelerate the application that you were talking about, whether that's finance or vehicle routing or in any case not anytime soon. And I can explain to you exactly why if you just give me an hour. Okay. And now I have like a new role, which is to tell people AI almost certainly will completely transform your application, but I can't explain why. So, uh, uh, so I feel like the difference between these areas, right? In quantum computing, theory has just been so far ahead of experiment, until very, very recently, as you're going to hear in this talk, when in the last few years we finally have experiments that are a challenge, at least, to simulate with classical computers, and that sort of directly engage the theoreticians like me. In AI, it's the opposite, right? Experiment is just way, way ahead of theory, right? And like we can do all of these things now. You scale a neural network large enough, and and train it on the whole internet, and it turns out that it understands English and it talks to you, and no one knows any principles by which to predict that would happen. Right, or to explain it, or to predict what's going to happen next when it's scaled up again. Okay, but so I'm going to talk about quantum computing, where at least often we do hope to prove things, as theorems, just from the rules of quantum mechanics. And we actually know a lot, both what can be done, what can't be done. Now, if you read the popular press, usually a quantum computer is just like a magic machine that does anything, right? It's just like the Oracle of Delphi or something, right? And indeed, when you search for pictures of quantum computer on the internet, you find things like this. I've been to some labs, and while I didn't understand exactly what I was looking at, that's not quite what they looked like. So. Okay, so what is quantum computing? I'm not going to belabor this because probably most of you have heard some talk about quantum computing before. But the goal is to build a computer that inherently exploits the rules of quantum mechanics. Okay, and why is that good? Why could that potentially help you? Well, it's because we have known for 100 years, right? We've known since the creation of quantum mechanics in the 1920s that quantum states are actually these immense objects, right? Like much, much larger than anything that's directly visible to us. Okay, like if I have 1,000 particles, right, and each one, let's say, can be in one of two states, let's say, spin up or spin down, for example, or as we might like to say in computer science, 0 or 1, right? We'll just give the two states some arbitrary labels, call it a bit. Okay, so now I have 2 to the 1,000 power possible states for those 1,000 particles. But now what quantum mechanics has always told us is that in general, to write down the state of those particles, I have to assign a complex number called an amplitude to every possible configuration that I could see when I measure those particles. Okay, so this is actually a vector in a 2 to the 1,000 dimensional vector space. Right, it's a list of 2 to the 1,000 complex numbers. Okay, if I'm going to use the Dirac-Ket notation, I could write it like this, where here n is 1,000. And so you could say, just to keep track of a small molecule, or just with like 1,000 degrees of freedom, nature off to the side somewhere has to maintain some scratch paper with 2 to the 1,000 parameters, which is more parameters than you could explicitly write down in the entire observable universe. Okay, and not only that, but every time something happens to this molecule, nature has to cross off all of those numbers and replace them with different numbers. Okay, this is at least this is what orthodox quantum mechanics says. This is, now. And so, you might say, like, that's a hell of a lot of effort for nature to be going to. And, if nature is going to all that work, like, why don't we try to make some use of it, right? Why don't, we've known for generations that this fact about this exponentiality in quantum mechanics makes it challenging to simulate using classical computers, right? But then, 40 years ago, a few physicists, such as Richard Feynman and David Deutsch, had the remarkable idea that if nature is giving us this computational lemon, why don't we make lemonade out of it? Right? Why don't we build computers that themselves would use these quantum mechanical bits, these qubits, right? And now I have lots of qubits. I can't just write down amplitudes for each qubit separately. I now have to write down in general amplitudes for the outcome, every possible outcome of measuring all of the qubits together. That's what entanglement means. Okay, and the number of such amplitudes will grow exponentially. And so then I get something that, at least in principle, might solve some problems exponentially faster than a classical computer can. At any rate, it seems like if I want to simulate this using a classical computer, then my simulation, or at least the obvious simulation, would have to be exponentially slow, because it would have to maintain the complete list of all of these amplitudes, or at least no one knows how to do it in a way that fundamentally avoids that. Okay, now, usually if you read about quantum computing in the popular press, it'll sort of get that far, sort of explaining what exponentials are, and that you have this exponential number of parameters, and then it will take this leap into nonsense, okay? And it will say, and therefore, a quantum computer is just like a normal computer, except it is massively parallel. It gets to try every possible solution at once. And you say, oh, well, of course that would be faster. That would be like faster for everything. Like, wow, that's, that sounds almost too good to be true, right? And indeed that is, that's not how it works. And and we've understood this since the early 1990s at least. Okay, the fundamental difficulty is that while it's true that you have this exponential list of amplitudes, sort of in the background to describe the state of a quantum system, you never directly see an amplitude, right? What you can do with a quantum state is measure it. Right? But measurement is inherently a destructive operation. Okay, when you measure a state, you force it to decide which outcome it's going to show you, right? And whichever one it picks, it collapses to that one. Okay, and the way it collapses is this famous Born rule that says that the probability is equal to the square of the absolute value of the amplitude. Okay, so now nature is just going to pick one of these x's randomly and show you that one. Okay, so, well, it's true that with a quantum computer, you could make an equal superposition over all of the, answers, all possible answers to your problem, even if there were 2 to the 1,000 of them. Okay, but now, if you just measure, not having done anything else, then all you're going to see will be a random answer. Right? And if you just wanted a random answer, I mean, you could have flipped a coin a bunch of times, right? You didn't need to spend the billions of dollars to build this quantum computer. Right? So the only hope of getting a speed up or an advantage from a quantum computer, the only point to building one is to exploit the way that these amplitudes, being complex numbers, work differently from conventional probabilities. Okay, probability is a real number from 0 to 1, right? But amplitudes can be negative or even complex. Okay, and the key point is that, in quantum mechanics, if I want to know the amplitude for some event to happen, like let's say a particle to hit a certain spot on a screen, I have to add up an amplitude from every way that that event could have happened. Okay, and if one of those contributions, let's say, is positive and another one is negative, then they can cancel each other out so that the total amplitude will be zero and that event will not happen at all, right? This is quantum interference. This is like the one weird trick of quantum mechanics that it just uses over and over again. Okay, so with every algorithm for a quantum computer, the key idea is we're trying to choreograph a pattern of interference such that for each wrong answer, each one that we don't want to see, some contributions to its amplitude are positive, others are negative. So on the whole, they cancel each other out. Whereas for the right answer, the answer that we do want, we want all the contributions to its amplitude to be pointing in the same way, right? So that they constructively reinforce each other. Okay, if we can arrange that, then when we measure, we're going to see the right answer with a large probability, right? And if we don't see it, we can always just run the whole computation again from the beginning, and until we do. Okay, but we're trying to boost the probability of seeing the right answer to much, much larger than any classical algorithm could have gotten it in a comparable amount of time. Okay, the tricky part is that we have to do this even though we ourselves don't know in advance which answer is the right one, right? If we knew, what would be the point, right? We need to choreograph this interference process, with some kind of mathematical guarantee that whichever answer is the right one, that is where the amplitude will be concentrated. And we have to do this, for it to be useful, faster than any classical algorithm could do the same thing. Okay, and in quantum computing research, that more than anything else is the sticking point, right? There are, like, at some point, people learned that they can just write papers or issue press releases where they just say, we used a quantum computer to do vehicle routing. We used a quantum computer to recognize handwriting, right? And that, in the press and investors and funding agencies would all eat that up with mustard. Okay, and so you have a whole, like thousands and thousands of papers that's all based on everyone agreeing to not ask the question, but did you beat what a classical computer could do for the same task? And if you didn't, then what is the point, right? So, and so like my blog, just, became like, widely read just because I just said this thing that, like people, were politely agreeing to not say. Right, and so that that was sort of like an easy thing to do. So so you have to beat a classical computer, right? And for a quantum algorithm to be useful. Okay, and this is this is hard. Okay, and it's sort of a minor miracle that we can ever do this for any interesting problems. Okay, so this brings us to the question of what will quantum computers actually be good for? Okay, and after more than 30 years of quantum algorithms research, I think unfortunately the two clearest examples of what quantum computers will actually be good for in the real world are kind of still the ones that we knew about in the 1990s. Right, we know a lot more detail about them, okay? But the two biggest things, number one, is it would give us a general purpose programmable simulator for quantum physics and chemistry themselves. Okay, this was the original application that Richard Feynman was after. And this is still, I think, the economically by far most important one that we know of, right? I mean, anytime you're designing a new material, a new drug, new, solar cells, batteries. I don't know for sure that a quantum computer would help you, but I can't rule it out. Okay, because simulating many body quantum mechanics problems is sort of exactly what this device was born to do. Right, and this is often important economically, and it is often classically very hard. Right, and we use supercomputers to try to get decent approximations, and it doesn't always work. Okay, Now, that's not the application that put quantum computing on the map for most of the world. That one was the discovery by Peter Shor 30 years ago now, that if you built a large programmable quantum computer, then you could use it to efficiently find the prime factors of large integers, okay, and solve various other problems in algebra and number theory, where you might say, okay, that's nice, who cares about those? Well, it so happens that almost all of the encryption that we currently use to protect the internet, I guess now and then, is based on the belief that those problems are hard. Okay, so if you built a quantum computer, then you could, basically all of the encryption that people use when you visit any website with HTTPS, or you ever send your credit card number to Amazon, or the signature scheme in Bitcoin, right? All of that could be broken. Okay, now that's a big deal, obviously, for intelligence agencies, for criminal syndicates. It's not necessarily a positive for humanity if you can do this, right? What it would mean in practice is that everyone would have to migrate to what we call post-quantum encryption. So we do have very strong candidates now for new public key cryptographic codes, many of them based on lattices, that seem secure, even against the quantum computer. No one has proven any of this stuff, but after 20 years, no one knows a quantum algorithm to break these systems. So we could try to migrate all of the servers in the world to these other crypto systems, and then we'd be back where we started. Okay, now the narrative that has sort of gone out to the press and funding agencies, in the last decade or two, has been all about how quantum computers are going to accelerate optimization, machine learning, combinatorial search, things like that. The truth is that we're going to have to be very lucky to see a quantum speed up for any of those tasks anytime soon. We do know of a quantum algorithm that is generally useful for those kinds of tasks. It's called Grover's algorithm. And what it generally does is it lets you solve combinatorial search problems in about the square root of the number of steps that a classical computer would need. Right? So that's a real speed up. Okay, but it's not exponential. It's only a square root. Okay, which means, now if you're going to be running a quantum computation, you're paying an enormous overhead to, to do error correction, which I'll, talk about later, right? And so now you need your square root speed up to win out over that factor of 1,000,000, right? And now your problem size has to be quite enormous before that happens. Okay, and then we have these other quantum algorithms where maybe you get more than the Grover speed up, but we're not really sure. Okay, we don't, the algorithms are heuristic. We can't really prove very much. And it might look like there's a big speed up for a while, but then someone improves the classical algorithm, and then the speed up goes away. This kind of thing has happened again and again. Okay, so, but now the truth is that for me personally, like none of these three are why I got into this field at all. Okay, for me, yes, right. For me personally, the +1 application has always been disprove the people who say that quantum computing can never work. Okay, or to put it more neutrally, test quantum mechanics itself in this entirely new regime. See if it's actually true that nature has this exponentiality underneath the surface. That when you talk about 10,000 qubits having this 2 to the 10,000 dimensional Hilbert space, is that just a mathematical abstraction, or can we explicitly see that has to be there in some sense because we used it to solve a hard problem that we couldn't have solved otherwise? So from the very beginning, there have been skeptics of quantum computing. And look, but you could say by some definitions, I'm a skeptic too, right? I'm skeptical of a lot of the claimed applications or the claimed timelines for it. but there are people who go further than that, and they say, no, I think this is fundamentally impossible, right? And you've just all the physicists and computer scientists have just like ignored. I've thought about it for 5 minutes, and we've discovered why quantum error correction can't work, right? There's that kind of and then there are people who actually raise a very interesting possibility. Maybe we will try to build a quantum computer, and instead we will discover that when it's pushed to this extreme, quantum mechanics itself will break down, that it is only an approximation to some better theory, right? And that the quantum computer is like a Maxwell's demon. It's like a reductio ad absurdum of quantum mechanics in this regime. Paul Davies, who is over there, has speculated in various articles that maybe when the number of amplitudes exceeds the number of bits that could fit in the whole observable universe, which is like 10 to the 122 power, and that should happen at about 400 qubits, that maybe something will change, right? Maybe we'll start to see a breakdown of quantum mechanics. That prediction may actually be testable in the very near future. Okay, my guess is that quantum mechanics is going to be fine, as it's been fine with every experimental test for the last century. But until we do the experiment, in some sense, we don't know, right? And like for me, the best outcome would be to discover that quantum computing cannot work, right? Because that's the outcome that's like Nobel Prizes all around, right? That's like overturns a century of physics. It's like the quantum computer working like it's supposed to. That's the more boring outcome. That's the more conservative outcome, right? But it's like either way, you've learned something about this new regime. Okay, so you could say, what is quantum supremacy? It's just doing an experiment where we try to directly target this quote unquote application. Okay, so there are many proposals for how you actually physically build a quantum computer that are all being pursued in parallel. You can use superconducting coils, which are actually almost big enough to see with the naked eye, but you cool them to about 10 millikelvin, and they superconduct, and you can put them in a superposition of two different states, and you could use Josephson junctions to entangle them, make them talk to each other, at least if they're next to each other, in this sort of two-dimensional chip. That's what Google has been doing, also IBM, also a group at Yale. You can use, for your qubits, you can also use the spin states of ions, like ytterbium nuclei for some reason. They suspend them in a magnetic field, they manipulate them with lasers. There's a company called IonQ in Maryland, also Quantinuum, which is a spinoff of Honeywell in Colorado, who are doing amazing work with this. You could also use neutral atoms. There's a group at Harvard of Misha Lukin and a spinoff company. Everyone's got a startup now, right? But theirs is called Quera. And by the way, like every possible acronym involving the letter Q has been taken now by one of these startups. I'm sorry to report, but they just had an amazing announcement a couple months ago that they can show the beginnings of quantum error correction. Microsoft is pursuing an approach that's sort of exotic, even by quantum computing standards. It involves creating these particles called non-abelian anyons that would sort of be naturally error resistant. So that's a huge advantage. The only downside is you have to engineer a new state of matter that's never been seen in nature. But they're trying to do that, and they've made a little bit of progress. And then you can use the states of photons as your qubits. Psi Quantum in Palo Alto has been pursuing that. Also a company called Xanadu in Toronto, also a group in China. Okay, so I don't know which of these approaches is going to succeed. Fortunately for a theorist, I can just root for all of them and hope that one of them does. But you might wonder, why is building a quantum computer so damn hard, right? Or like, it's been 30 years already. Where is your home quantum computer, right? Now, I think we should kind of calibrate expectations. I mean, Charles Babbage wrote down the basic principles of classical computing in the 1820s. Right. And from then until the invention of the transistor was more than a century. Okay, I think we'll be able to beat that, time frame. Okay, but building an entirely new technology, this is a work of decades or generations. And the truth is, like, compared to when I started in quantum computing 25 years ago, it is insane what the experimentalists can now do. Right, like, but in the 90s, it would be if you could do a gate to interact 2 qubits with like 50% fidelity, that would be a Nature paper, right? And then the 50% became 90%, became 95, became 99%, and now it's like 99.9% in the latest experiments. Okay, but you might wonder, so what the skeptics said from the beginning is, well, you're never going to have perfect control over quantum systems, and that seems like a killer, because the trouble is, these quantum superpositions, involving these vectors of amplitudes, these are extremely fragile objects, right? It doesn't just have to be a person who is looking that collapses a superposition. It can be any kind of interaction between the qubits and their external environment. If that interaction carries information away about whether that qubit was a 0 or a 1, then it will be exactly as if someone measured the qubit, right, and collapsed it to either 0 or 1. Okay, which means that if I want to build a useful quantum computer, I have to keep my qubits ridiculously well isolated, right, from everything, all the radiation and all the modes in the external environment. But they can't be perfectly isolated because they have to interact with each other. And we have to be able to go in and tell them exactly which qubit should be interacting with which other qubit and how and when, right? And so, this is so hard that some people said, you will never do this, right? It's like Maxwell's demon. Okay, but what changed most people's mind was a remarkable discovery in the mid-90s, which was called the quantum fault tolerance theorem. And basically, what this said is that you don't have to get the rate of measurement, decoherence as it's called, all the way down to 0, interaction with the environment. You merely have to make it very, very, very small. Okay, and if you want a concrete number, the best current estimates suggest that if you can merely get 1 more 9 than the current experiments have achieved, so if you can do like 2 qubit operations with 99.99% accuracy, then this should be enough that now you can encode the stuff you care about across the collective states of many physical qubits using these very, very clever quantum error correcting codes. And you can do it in such a way that even as your physical qubits are all leaking into the environment at some rate, you can monitor that, you can see as it's happening, and you can apply correction operations to preserve the quantum information that you actually care about. And in this way, you can simulate noiseless qubits, okay? And you can do as long of a quantum computation as you want on as many qubits as you want. So, once you've passed this fault tolerance threshold, it's as if you've passed like the critical mass for a nuclear reaction, right? Like if you're halfway there, it's not half as impressive. Okay, you have to get to the point where, as you're doing error correction, you are making things better rather than making them worse. Okay, and we are not at that point yet, but after 25 years of experiments, like if you just look at it on paper, we're about an order of magnitude away, right? So that's if you just look at those numbers, then you can feel kind of optimistic about it. Okay, but it's true that we're not there yet. Okay, so and maybe we won't be there for some years, unless maybe GPT-5 achieves super intelligence, and then if it wants to build the quantum computer, it will. Except maybe if it wants to kill us all, it'll do that too. Okay, so So this brings me to quantum computational supremacy. And this is a term that was coined by the physicist John Preskill in 2012 to describe something that several of us had been thinking about before that. But we didn't come up with such a catchy name for it. Okay, and at first I didn't like this name when I first heard it, but it caught on with people for some reason. And what Preskill meant by this was just the use of a quantum computer to solve some well-defined problem much faster than any available classical computer running any known algorithm. And notice that I did not say a useful problem. Okay. Uh, so, problem doesn't have to be useful, but it can't just be, here's this complicated pile of stuff in my lab, and my problem is to simulate this, right? Because then, you've sort of munged together computational difficulties with just the mundane difficulties of characterizing your physical system. So no, that's not going to count. I need an independent mathematical definition of what is the problem to be solved that I could just as easily put onto my classical computer. And the only issue is that with the classical computer, the calculation is going to take too long, right? And with the quantum computer, because of the exponentiality of the amplitudes, because of the dimensionality of the state space, I can see that I am solving the same problem much faster. Okay, so I want to see, an actual observed speed up, like I'm doing something in seconds that, with the best classical algorithm is going to take me, hours or days, or it's going to take me some enormous cluster of GPUs that'll, I'll have to spend a fortune in electricity or in AWS credits or whatever. And I want this to be for a problem where the quantum algorithm actually has better theoretical scaling behavior. So like the quantum running time is only increasing as the size of the problem raised to some fixed power, like polynomially, whereas the classical running time is increasing exponentially with the size of the problem. Ideally, I want to see an asymptotic separation like that one. And then thirdly, I want the observed speed up to be because of the theoretical asymptotic speed up. I want to rule out any explanation other than that one. Okay, that would be my definition of quantum supremacy. Okay, so now we come to, how should we achieve quantum supremacy? And you might say, well, look, why not just run Shor's algorithm to find the prime factors of some 4,000 digit number, right? That I chose to be a product of 2,000 digit primes, right? And if Shor's algorithm succeeds at that, well, the great advantage, it's very easy to check the result. At least with a computer, you just multiply the alleged factors together. We even know fast methods to check that they're prime. Okay, and so then you're convinced. Okay, I guess either you really built a quantum computer and it really worked, or else you have some crazy factoring method for a classical computer. But either way, you have changed the world, right? So it's a very convincing demonstration. The trouble is, running Shor's algorithm to factor any interesting size number almost certainly will require a fault-tolerant quantum computer. And as I said, we don't have that yet. Okay, and probably fault-tolerant quantum computer, would need hundreds or thousands of physical qubits to encode each logical qubit. So like if you need Shor's algorithm with thousands of logical qubits, now you're talking about millions or hundreds of millions of physical qubits, okay? And now it starts to look like a Manhattan Project, right? Like maybe you have to fill a whole building with dilution refrigerators, and then maybe you can do that, okay? Or someone comes up with a better idea, okay? But what can we do, soon, like in the more immediate future? So some of us, back in 2010 or so, started thinking a lot about that kind of question. And my former student and I came up with something called boson sampling, that then other people had similar ideas. And then But let me show you sort of a variant of these ideas that ended up being what Google actually did. Once, like in 2015, they put together an experimental group, like 75 people in Santa Barbara, to try to actually do, the kind of quantum supremacy experiment that we had proposed. Okay, but what they did was called random circuit sampling. Okay, and this is where basically I imagine I have a set of qubits that I can do programmable operations on, let's say 50 or 60 of them, and now what am I going to do? I'm going to start all my qubits in the 0 state, so they're all initially 0, and now I'm just going to do a random sequence of gates. Okay, so in the Google architecture, like each qubit can talk to its nearest neighbors in a two-dimensional lattice. So it looks like this. Okay, and now I'm going to just let the couplings be chosen randomly from some set. And so now, and I'm just going to layer a whole bunch of these, layers of randomly chosen operations. And what does this produce? Well, it produces some kind of mess. Okay, it produces some kind of, complicated entangled state of all of my qubits. And now what am I going to do? I'm going to measure that state. I'm just going to ask each qubit, are you 0 or are you 1? Okay, if I do that, I'm now just going to see a random string, let's say a 50-bit string. Okay, and I can run again and again with the same, over and over with the same circuit on the same initial state. And each time I'm going to see another independent sample from that same probability distribution. If the circuit is C, let me call the distribution D sub C. Okay, so I can generate a bunch of independent samples, let's say K of them, S1 up to Sk, from that distribution. Okay, and now, what can I say about this distribution? Well, probably every string will be exponentially unlikely. Okay, right? So like I could run my quantum computer for, years and years and never see the same output twice. Okay, so this is not a problem like factoring that has a single right answer, right? This is a problem where the output is going to be, the desired output is different every time, right? But crucially, this is not just sampling a purely random string. Okay, there are little inhomogeneities. Some outputs should be likelier than others. Okay, now why is that? Well, if I just think about a random quantum state, or producing one, well, for some of the output strings, there was a little bit more constructive interference. And for others, there was a little bit more destructive interference. Okay, and so like the average probability, of all of my 2 to the n strings is of course 2 to the minus n. Okay, but for some strings, it's going to be twice that. For others, it's going to be half that. So it'll be 2 times 2 to the minus n, or 0.7 times 2 to the minus n. Okay, and actually, the probabilities themselves will look like exponentially distributed random variables. You can prove this with a mean of 2 to the minus n. Okay, so now suppose I do this a bunch of times. I collect all of the outputs, and now I know what circuit I used. And now using my classical computer, and using a lot of classical computation time, I go and I can now apply a statistical test where I ask the question, were the outputs that I observed preferentially concentrated among the ones that quantum mechanics predicted were more likely? Okay, so I can do statistics on the outputs to check whether my quantum computer was working correctly. Okay, and the statistical test that Google applied in its experiment was just one of the simplest ones that you could write down. They called it the linear cross entropy benchmark. It's not actually about, forget about the name, okay? But all they did is for each output S sub I that they observe from the quantum computer, they calculate the probability that an ideal quantum computer running this circuit C would have produced that output. Okay, that's this squared absolute value here. And then they just add all of those numbers up. Okay, and then they see, does the sum exceed some threshold or not? Okay, and if it exceeds the threshold, then we say, the test is passed, and otherwise not. So it's if for those of you who have seen the Bell inequality, it's kind of like that, right? It's a sum inequality that you have to violate. Okay, now our expectation, and one of the things that my students and I did was to give some theoretical computer science justification for this expectation. But we think that with a classical computer, running in polynomial time, you should basically only be able to guess random strings that are just barely even correlated at all with the quantum computer's output. In which case, each of these numbers will be about 2 to the minus n. I add up k of them, I get k over 2 to the n. Okay? Now, if I had a noiseless, perfect quantum computer, then you can do a calculation that says that the sum will, on average, be about 2k over 2 to the n. Okay, so it's exactly twice the trivial value. Okay, so trivial would be b is 1, perfect quantum computer would be b is 2. Now, if you're wondering what Google achieved in its experiment, it's now famous quantum supremacy experiment, they achieved b equal to 1.002. Okay, so just tiny, tiny bit above the classical number. Okay, so basically they have a lot of decoherence that is like sort of, making their output string almost completely random, but not quite. Okay, there's still a little inhomogeneity that you can still observe. That's that one, that's that 0.002. And they did check, to like 15 sigmas or whatever, that yeah, that really is 1.002. It really is bigger than 1. Okay, so that was what they did. And so now the current situation is this random circuit sampling kind of experiment. Google first reported it in 2019. Since then, they've done better ones. There's also a team at USTC in China that did a very similar experiment with up to 60 qubits. And then the team at USTC and also a team at Xanadu have now also demonstrated this sampling-based quantum supremacy using our original proposal, which was called boson sampling. This one is not based on qubits. It's based on generating a bunch of photons, sending them through a network of interferometers, beam splitters, phase shifters, just passive optical devices, and then measuring where the photons end up. Okay, and we look at the probability distribution over all the possible places where the photons could end up, the lists of occupation numbers, in other words, and we argue that that distribution also looks hard to sample with a classical computer. Okay, I could go through the reasons why we believe these problems are classically hard, but then I'd have to talk about a bunch of complexity classes, and since this is a physics colloquium, I'll only do that if I'm asked. Okay, so you can do this with building an optical table. That's what USTC did. You can also just do all of this on an optical chip. That's what like PsiQuantum is doing. So okay, so it sounds like so a lot of people drew the conclusion in the last few years. It sounds like quantum supremacy is a done deal. Sounds like we've now proved that we can do an experiment where we beat a classical computer, and so now people kind of lost interest in this, and they said now we just want to go straight for quantum error correction, for building a full because none of this is actually error corrected, right? This is all like doing what you can with 50 or 60 bare non-error corrected qubits before everything falls apart. Right, but we know that if you want to scale way beyond that to thousands of qubits or whatever, then you're going to need error correction. So now many people say let's just concentrate on that now. Okay, but I'm here in the remaining 10 minutes or so to tell you why I think quantum supremacy is not a done deal. Why there's more to do. Okay, so what is wrong with the current experiments? All right, well, they're not error corrected, and because of that, we can't really scale them up. we're stuck at like maybe 60 qubits, maybe a few thousand operations. We can't go to thousands of qubits or millions of operations. Okay, that's obvious. Okay, but now deeper than that, it turns out that classical computers can actually do these sampling tasks better than many people hoped, or better than people knew back in 2019. Okay, so they've developed algorithms which are still exponential time. So they're still, theoretically, they have, exponential scaling, but for the problem sizes that like Google and the others are working with, they can actually do it pretty feasibly. Like, maybe if I have a big, a reasonable sized GPU cluster, then maybe it just takes me, a few minutes, right? And maybe, you could say some quantum supremacy remains because, I'm still, for my GPU cluster, it's drawing like 100 times as much electricity as the quantum computer is drawing. And that's even counting the dilution refrigerator. Okay, but a factor of 100, that's kind of chicken feed by computer science standards, right? We would like a much bigger separation than that, factors of 1,000,000 or something like that. So then you could say, well, why not just scale at least to 80 qubits, to 90 qubits, and then we should be able to see a much clearer separation between quantum and classical. Okay, but now we come to maybe the most fundamental drawback of the current paradigm of quantum supremacy experiments, which, I have to take some of the blame for, but like I and others have been unable to do better than this. The issue is that again, even just to verify the results of these experiments, just to check the quantum computer's work, that seems to already take exponential time for a classical computer, these experiments, right? And for reasons that are just inherently connected to why we think that spoofing the quantum computer would take exponential time for a classical computer. So like if you improve one, you improve the other, right? So which means that you can't scale to way beyond the regime where any classical computer could ever keep up, because if you did, then you would also scale way beyond the regime where a classical computer could even check the answer. And so where you could even prove what you did. Okay, so as long as we remain in this world, then any quantum speed up that we can demonstrate is going to be sort of fragile, tenuous, right? It's going to be vulnerable to the very next advance in classical computing or classical algorithms. Okay, so this is the way that I think about where we are and where we need to go. Okay, so yet another term coined by John Preskill is NISQ, noisy intermediate scale quantum, right? And this again caught on for some reason, but it just means all the quantum computations that you can do with like devices that look like the existing ones that are not fault tolerant. Right, so like this is like the quantum computations that are practical to do now. Okay, so we want something that is NISQ. But then we also need something with an in-principle quantum advantage, where we actually believe that as you scale, you beat a classical computer, hopefully by an exponential factor. Okay, and then thirdly, as I just told you, we want something where a classical computer can efficiently verify the result. Okay, and I claim that the current situation, if you squint, is basically that we can achieve any two of these three requirements. Okay, so if you want something that's NISQ and that has a quantum advantage, that's like the current generation of quantum supremacy experiments. If you want something that's efficiently verifiable and that gets an in-principle quantum advantage, I mean, Shor's factoring algorithm was always like that. And we have many other examples. We just can't implement them with current devices. And then if you want something that's NISQ and efficiently verifiable, all this stuff about quantum machine learning and optimization will happily fill the bill, except that we don't actually know that any of it beats a classical computer. That's the problem. So how can we get to the center of this Venn diagram? Right? We could try starting with this heuristic stuff and then trying to actually show a quantum advantage from some of it. We could try starting with Shor's algorithm or the things that like we're very confident get these exponential speed ups, and then figure out how to implement one of them on a NISC device. Or, and this is the direction that I've thought about the most, we can start with the quantum supremacy experiments that already work and then figure out how can we make them efficiently verifiable. Okay, so let me give you, an open question that I've been, pondering for the last couple of years. Okay, so if I'm given a quantum circuit C, let me call it peaked if it has the following property. Okay, that there is, when I run C on the all zero initial state and then I measure, there is some particular output string, call it X, that occurs a very large proportion of the time. Like, let's say at least 10% of the time. Okay, most quantum circuits are not peaked, right? Like, they're like much more even among the exponentially many outcomes. But I want to just consider the tiny fraction that are, where the probabilities of the outputs are concentrated, on some single outcome. Okay, and now I want to imagine that I pick a random quantum circuit, just like we do in the existing quantum supremacy experiments, but now I throw the circuit away unless it happens to be peaked. So in other words, I condition on the event that my circuit is peaked, right? I post-select. I keep only the peaked ones. Okay, and now I ask, what can we say about a random quantum circuit that is peaked? Okay, so now, there are two sort of extreme possibilities. One is that the circuit would basically be trivial. So for example, one way to get a peaked circuit is to just apply a whole bunch of gates and then apply the inverses of those gates. And then that'll just return me back to the all zero state. It'll be just a complicated way of doing nothing, right? Okay, so, if it was that, that wouldn't be very interesting, right? But a different possibility would be that the circuit would look for all the world like a truly random quantum circuit. I wouldn't be able to find any structure in it, no matter how much I examined it with my classical computer, right? But only by running it on a quantum computer would I see that, this circuit is peaked. Because, I would see that some output just keeps occurring over and over again. Okay? If we were in the latter case, then I claim that these circuits would be the kind of thing we want for a near-term verifiable quantum supremacy experiment, right? They would look like random circuits, but the problem of distinguishing them from truly random circuits would be hard for a classical computer, and would be solvable using a near-term quantum computer. Even then, this would still leave the problem of how do we actually find these circuits in any reasonable amount of time, right? I still haven't answered that question, okay? But at least we would know that those circuits are out there platonically, right? They exist. We would, it would remain only to construct them efficiently, okay? So, I don't know the answer. We can ask many related questions. Given a random circuit, how many more gates must we add to the end in order to make the circuit peaked? If I start with m gates, I can always add another m to get a peaked circuit by just inverting all my original gates. But is there anything substantially less than m? Could I add m over 2 gates to get a peaked circuit? I don't know. What fraction of quantum circuits are peaked? How hard is it to sample a random peaked circuit or a pseudo-random peaked circuit? So with a grad student, Yushuan Zhang, we did some numerical studies of this. And what we found is that there are circuits with a surprising amount of peakedness. So here, n is the number of qubits. And this is the amount of peakedness that we were able to find by starting with like 100 gates and then adding like either 50 or 33 or 25 gates onto the end of it to try to optimize the peakedness. And on the one hand, you can see that we were able to get circuits that are pretty peaked, that have like some output that's occurring like 25% or 10% of the time. On the other hand, the amount, this is a log scale, the amount of peakedness seems to be decreasing exponentially with the number of qubits. Okay, so this says like, yes, there is some interesting peakedness that already we don't know how to explain analytically, but it seems to be decaying exponentially with the number of qubits. So, I don't know what's the ultimate truth of this. I'm going to skip this and I'm going to skip this because I'm out of time. But yeah, there are like other approaches where instead of verifying that you would do something that's hard for a classical computer, you would just try to directly verify the large dimension of the Hilbert space. Like I'm going to do something with 10 qubits that, in any classical explanation for what was going on would have needed at least 100 classical bits or something like that. And I'm actually working, that sort of experiment actually ought to be feasible right now. And I'm working with Quantinuum in Colorado to try to do that kind of demonstration now. So I can, talk about that if people are interested. But since I'm out of time, let me just go to the summary, which is, exponential quantum speedups that are easily verifiable with a classical computer tend to be somehow weird or finely tuned, as we see with the factoring problem, right? In order to design his algorithm, Shor really had to exploit very, very special properties of factoring that don't seem to carry over to machine learning or optimization or most of the hard things that we want to do with computers. Okay, so if we want to demonstrate a totally unambiguous speed up on a near-term quantum computer without error correction, we'll have to somehow make it as generic as possible. And this takes us all the way back to the beginning of quantum computing theory, to the question, just how generic can we make a speed up? I mean, if nothing else, there's always quantum simulation, but can't we do better than that? All right, thanks.